Assalamu alaikum. Welcome, dear students, to the course of Electric Machine 2, lecture number 7. Today we are going to discuss an important topic, that is synchronous impedance method. If you people not see or learn the last class, try to learn that as we are going step by step. So let's start synchronous impedance method. For this, the following data are required, that is armature resistance, open circuit characteristics and short circuit characteristics. Now, what is armature resistance? The armature resistance Ra per phase is determined by using direct current and the voltmeter ammeter method. This is the DC value. The effective armature resistance AC resistance is greater than this value due to skin effect. It is usual practice to take the effective resistance 1.5 times the DC value. So in armature resistance, we use the method voltmeter ammeter method. We measure the armature resistance as it is the DC value. So the effective value of the armature resistance is equal to 1.5 times the DC value. It is due to the skin effect that is present in AC circuit. Now, measurement of resistance. Resistance are classified into three categories for the sake of measurement, and different categories of resistance are measured by different techniques. They are classified as low resistance, medium resistance and high resistance. Resistance having value below than 1 ohm, we categorize it as a low resistance, and then a medium resistance value is between 1 ohm to 0.1 mega ohm, and high resistance value is above 1.1 mega ohm. So different techniques are used for resistance measurement, that is ammeter voltmeter method, Wheatstone bridge method, ohm meter method. In this we are studying ammeter voltmeter method, mean we connect ammeter and voltmeter, which give us the reading of current and voltage, from which we can find resistance R. Now the second one is open circuit characteristic, OCC. It is actually the curve between armature terminal voltage on open circuit and the field current when the alternator is running at the rated speed. This is the diagram of an alternator. This is the field circuit, this is the armature circuit. It is kept open and we measure the voltage across the terminal, the phase voltage. Here is the DC supply to the field current and a rheostat resistance. We can control the value of IF, field current, from this resistance. When we supply a DC to the field current and move it with the help of a prime mover, due to IF, flux is generated that is linked with the secondary winding, the stator winding, and EMF induced in it is its terminal are open, so we can find the voltage through voltmeter. This is the graph. It is between the EMF induced, voltage induced, and field current IF. Starting from 0, when we increase the field current, the EMF or induced voltage is also increased. Then a point reached, that is called a saturation point. After that, the curve starting to go towards down or start towards the constant value. Even after we increase the value of IF, the EMF induced remain the same. So this is the OCC of impedance method. Here in this we determine the OCC of an alternator. The alternator is run on no load, mean no load is connected to the stator at rated speed. The field current IF is gradually increased from 0 by adjusting the field rheostat as discussed until open circuit voltage E0 is about 50% greater than the rated phase voltage. The graph is drawn between open circuit voltage value and the corresponding value of IF field current. Second is the short circuit characteristic. It is the graph between short circuit armature current and field current. In this short circuit characteristic, the field circuit remain the same as in previous case. The armature circuit is short circuited and we measure the I short circuited in the armature circuit with the help of an ammeter. So short circuit characteristics is the graph between IF and I short circuited current. It is a straight line, mean when we increase the field current, the short circuit current in an armature increase. So in a short circuit test, the alternator is run at a rated speed and the armature terminal are short circuited through the identical ammeter. Only one ammeter need to be read, but they three are used for balance purposes. The field current IF is gradually increased from 0 until the short circuit armature current I short circuited is about twice the rated current. Now synchronous impedance method. In this method of finding the voltage regulation of an alternator, we find the synchronous impedance ZS and hence synchronous reactance XS of the alternator from the OCC and SSC. For this reason, it is called synchronous impedance method. The method involves the following step. We study open circuit characteristics and short circuit characteristics. With the help of these graphs, we find the synchronous impedance ZS and synchronous reactance of the alternator. Plot the open circuit characteristics and short circuit characteristics on the same field current base is shown in figure. This is the graph. This is the same field current that is common in both open circuit characteristic and short circuit characteristics. This is the voltage at open circuit and this is the current at short circuit. We consider a value IF So at this value we have a voltage that is denoted from E1, and it is the open circuit voltage. At this value we have a current value, that is short circuit current value, IS. Sorry. So consider a field current IF. The open circuit voltage corresponding to this field current is E1 as shown in the graph. The short circuit armature current corresponding to this field current IF is I1 or IS. Voltage E1 is being used to circulate the short circuit armature current I1 against the synchronous impedance ZS. As we all know, synchronous reactance is equal to under root ZS square minus RA square. The third point, armature resistance can be found as with the help of this we can find the resistance value. Once we found RA resistance on the armature side and XS reactance, synchronous reactance, the phasor diagram can be drawn for any load and for any power factor. The phasor diagram for the inductive load is shown. This is the phasor diagram of an inductive circuit. We have IA, armature current, as a reference voltage. As it is for the inductive circuit, the voltage will lead from the current, and this is the drop IA RA in phase with current, and this is the reactance drop leading from IA, and the sum IA XA plus IA RA plus V is equal to output voltage at no load. So the phasor diagram for the inductive load is shown. The load power factor being cos F lagging. Note that in drawing the phase diagram, current IA has been taken as a reference as discussed. The IARA drop is in phase with IA, where IAXS drop lead IA by 90. The phasor sum of V, IARA and IAXS is equal to E naught is equal to OB square plus BC square. That is OB square and BC square through Pythagoras theorem. That is OC is equal to OB square plus BC square under the root. We know that OB is equal to V cos angle plus IARA, and BC is equal to V sine angle IAXS. So from in this way we can find the voltage regulation of an alternator, that is the no load voltage minus full load voltage divided by full load voltage multiplied by 100. This is the phasor diagram. Now let us consider a simple example. Find the synchronous impedance and reactance of an alternator in which a given field current mean IF produce in armature current of 200 ampere on short circuited and generate EMF of 50 volt on open circuit. The armature resistance is 0.1 ohm. What induce voltage must the alternator be excited if it is to deliver a load of 100 ampere at power factor 0.8 lagging with terminal voltage of 200 volt. So X of S, that is synchronous reactance is equal to Zs square minus Ra square. The value of impedance is given, that is 0.25 square minus, that is the value of resistance. By simplifying it, we got 0.23 ohm. Now IRA is equal to 100 multiplied by 0.1, the value of resistance, which is equal to 10 volt. Then a drop in a reactance circuit, I into X of S, that is 23 volt. Cos of angle 0.8, lagging is given, that is 0.8, so we can find sine angle 0.6. And then E naught, we're putting the value in the equation E naught, so we got this, and by putting the value we got the value 222 volt. So go through this example and the example after this in the book. If there is any issue, to inform me.